All right, next in section 13.5, we're going to look at question number 5 on the worksheet. So here it says to consider the surface z is equal to 2x squared plus 3y squared plus 1. Imagine that you're walking along the surface directly above the unit circle c, which is parameterized as cosine t sine t, and we're letting t go from 0 to 2 pi, in the direction of positive orientation. So part A asks, on what intervals are you walking uphill? And B, what is your maximum altitude along the path? What is your minimum altitude? Okay, so first, before we jump into calculations, I'm going to pull up some visuals here. So right here, I just have our unit circle in the xy plane. Okay, and then we are looking at this surface, right, which is a nice paraboloid. It's not circular paraboloid. The cross sections parallel to the xy plane aren't circles because we have a 2 in front of the x squared but a 3, so they're actually ellipses. But in any event, nice looking surface here. And what we're doing is we're going to walk along the path on the blue surface that falls directly above the orange unit circle here. So you can imagine projecting the circle up onto the blue surface, and that's going to define our walking path. So that's going to look like this, okay? And then as far as when the positive orientation part, right, what is that referring to? So let's say, for example, I'm right here, and I'll zoom in a bit, on our path, okay? Now, the projection of our point, our location onto the xy plane would just give us this point here down on the unit circle. And when they're saying positive orientation, well, if I say take the view like this, and I'll go ahead and get rid of this stuff for the moment. If I'm just looking down on the unit circle, right, here's the x-axis and the y-axis, right, you know from pre-calc that, right, positive orientation is defined to be a counterclockwise rotation, right? So if I go ahead and rotate like that, that's what they mean by a positively oriented motion there. So coming back now to our original view, okay, here's our surface, here's our path, right? Our point is like this. So when I hit play, right, we're just rotating counterclockwise around that unit circle, looking down on the circle, and that is in turn determining my motion. Okay, cool. So now when we're asked in part A, on what intervals are you walking uphill? Right, well, downhill, uphill, up, and then down, up, and then down, right? That's what we're looking at. So let's go ahead now and do some calculations to figure that out. So here's our setup, right? We have z, our altitude on the surface. That depends on our position, x, y, right? But since we're restricting, right, our motion to be just directly above the unit circle c, x and y in turn depend on time, right, t. And so if I want to go ahead and find the rate at which our altitude z changes with respect to time, well, in the usual way, I can go ahead and just compute this using our chain rule, right? So we got del z del x, dx dt, and then we got our del z del y, and our dy dt. And so then I can go ahead and say that dz dt is equal to, well, the product of the rates in blue times dx dt plus product of the rates in green. Okay, and now to compute these, well, here's our equation for the surface. Z is 2x squared plus 3y squared plus 1. So del z del x would be what? Just 4x in that case. Not too bad. Then we're going to multiply that by dx dt. Now keep in mind, since we're sticking just to the unit circle here, x is cosine. So its derivative would be negative sine. Okay, then I'm adding to that del z del y. That's going to be 6y. and then I'm going to multiply that with dy dt, and right, y is just the sine of t, so its derivative would be cosine. Okay. So now what I'd like to do is just write everything in terms of t, right? Because for a question like A, when it says on what intervals are you walking uphill, right? This is a reference to time, t, right? So it's going to be easiest to answer that if everything here for the derivative is in terms of t. So let's just go ahead and substitute in cosine for x. So that's going to give me 4. This would be cos times minus sine, and then I'm going to substitute in sine of t in for y, so this would be 6 sine of t times the cos. And now notice here I have a sine t, cosine t in each one of these terms, right? And so I have minus 4 of them here and 6 of them there, so that comes out to be 2 times the sine of t times the cosine of t. Okay, now it's going to be a little simpler if I go ahead and take advantage of the following identity, right, for the calculations to come. This isn't totally necessary. You could still proceed without doing this, but using what we call the double angle identity. So in other words, trading in 2 sine t cosine t for just sine of 2t, it's going to make our lives a little simpler. Okay, so this then is our derivative dz dt. Okay, nice. So now if I want to know where am I walking uphill, well, that's going to be when my altitude is increasing, which would correspond to when this derivative dz dt is positive. Okay, and to find, say, intervals where a derivative is positive or maybe negative, a good way to do that is to start out by finding where is your derivative equal to 0. So what I'm going to do now is set this derivative, which is just simplified down to sine of 2t, equal to 0. And now I want to solve this equation. And here, just recall, right, if the sine of anything is 0, right, that happens when that input is equal to what? Well, any integer multiple of pi. So say 0, pi, 2 pi, 3 pi, so on and so forth, okay? So here, if I'm taking the sine of 2t, and that's equal to 0, that's going to imply that 2t, the input for the sine, is equal to 0, pi, 2 pi, 3 pi, so on and so forth. And so then for t itself, we'll just divide through by 2, and we're going to get that t can be 0, pi over 2, pi, 3 pi over 2, and then I'm going to stop here at 2 pi, right, because again my interval here t is restricted there from 0 to 2 pi. Okay, cool. All right, so that's really, really nice. Now what I'm going to do over here, make a little space, I'm going to go ahead and just create a little derivative diagram for us. Okay, so this is just going to help us organize, right, where the derivative is 0 and then where it's positive and where it's negative. Okay, so here's our derivative, and we just found at these times, so 0, pi over 2, pi, 3 pi over 2, and 2 pi, right, our derivative is 0. So now what I can do is look at, say, an intermediate time. Like let's say, for example, I was at the time t is equal to pi over 4. Okay, what I'm going to do is plug in pi over 4 into my derivative to see if the derivative is positive or negative. Okay, so to do that, well, dz dt would be what? I'm going to go ahead and plug pi over 4 into the simplified version, which is just the sine of 2t. And doubling pi over 4 would give me pi over 2. So I'm going to take the sine of pi over 2 and that's, of course, 1. But in particular, what I really care about is that this is a positive number, right? So I get a positive derivative on the interval from 0 to pi over 2, indicating then that z, the altitude, will be increasing. Okay, so then you're going to do the same kind of thing on these other intervals, and I'll just go ahead and tell you, right, that you're going to get a negative derivative on this next interval, and then it goes back to positive, and then it goes back to negative. Okay, cool. So now let's go ahead and answer part A, right? We're going to be walking uphill when? Well, when t belongs to, remember that script E notation, what intervals? Well, when we're here, right, with a positive derivative, right, that's when our altitude will be increasing. So that'd be from 0 to pi over 2, not including the endpoints. And then I'm going to use a union symbol, and that'd be pi to 3 pi over 2. Okay, cool. So that would be part A. Part B, then, we're asked to find the maximum altitude and the minimum altitude. So let's look at, say, max altitude first. And so for this, I can see from my derivative diagram that I'm going to have a local max at pi over 2 and at 3 pi over 2. And those could be, of course, absolute maxes. It would be nice, right, to figure out z to know what x and y were at those times. And we can do that by just using, right, our parametric equations for the circle, right? So, for example, when t is pi over 2, if I plug in pi over 2 for x, I'm going to get 0. So here I'm saying my xy coordinates at pi over 2 would be x is 0, and y would be the sine of pi over 2, which would be 1. Now that makes sense, right? We're just saying we're at the top of the unit circle when our time is pi over 2. Okay, now at 3 pi over 2, our xy, this would be 0, negative 1, right? Plugging in 3 pi over 2, we're just at the bottom of the unit circle. So here we're saying we're going to have a max altitude when we're hovering over the locations 0, plus or minus 1. Okay, now to find z, the altitude, right, when we're at a maximum, we can now just plug in 0 for x into our surface equation, and then either 1 or negative 1, and because of the square, we're going to get that same output here. So we're going to get what? 0 plus 3 plus 1, so it's going to have a max altitude of 4. Okay, then for the minimum altitude, pretty similar. We can see from our derivative diagram, again, that we have minimums where? At pi, we're on the left side of the, sort of the left corner, so to speak, of the circle. So negative 1, 0. At 2 pi, that would be at 1, 0. And then at 0, which would be also at 1, 0. So here, right, our xy coordinates will be hovering over, would be plus or minus 1, 0. And so for that, we'd be saying, right, for our minimum altitude, this would be z is equal to, well, plug either 1 or negative 1 in for x. That's going to give you just a 2 there because of the square on x. 0 for y, so this is going to be 0, plus 1. So we're saying our min altitude then would be 3. Okay, great. Now real quick, before we finish, let's just go back to this diagram. Does that agree with what we're seeing? Well, yeah, you can see the z-axis there inside the surface. That looks like, yeah, the minimum altitude there happens here and here at a height of 3, and then our maximum of 4 happens over here and here. All right, great. That's going to do it for this problem.